This is Steve from Wallaroo.AI, and today we're going to take a look at how Wallaroo.AI together with Loft Orbital were able to successfully deploy a computer vision model meant for detecting naval activity to a satellite in orbit and downlink crucial insights for consumption by the US Space Force. First, let's talk about the architecture for this solution. We start on the ground with our Wallaroo Operations Center, which will automatically package up my models and then publish them out to a container registry for deployment. I can then uplink those model container images to my satellite on orbit, which is running a custom application that will make use of these models that have been deployed on the edge. Finally, we send our key insights and full-size images as well as model diagnostics to the ground as bandwidth allows. Here, I can see an RGB image of the Port of San Diego. This is what the pre-processed images that our models are expecting will look like, and we go ahead and use an ensemble of two models in order to identify all of the ships in this image. From there, we can rapidly downlink the key insights such as number of ships and the image chips of those ship detections. This will allow me to process these raw images on the edge and rapidly get the insights from them without having to downlink these large high-resolution images to Earth before analysis can even begin. Now, let's see how we were able to use Wallaroo to deploy these models to run on orbit. In order to get these models deployed, I open up my development environment, and you can see here I go ahead and import my Wallaroo SDK, which is a normal pip installable Python library. I then create a client connection to our installed Wallaroo instance on the ground using its location, and then finally set a workspace for my project that I'm working on. Now I can upload my models to Wallaroo for automatic packaging. We use an ensemble of two models for this, including one YOLO model and one SSD Lite model with a MobileNet v3 backbone, both of which are saved in an ONNX format. And so I'm able to give Wallaroo these model artifacts as well as the knowledge that they are of the ONNX framework, and they will automatically be packaged for deployment. Next, I specify my deployment configuration, which specifies what hardware will be allocated to each of these deployments, in this case 1 gig of memory and 2 CPUs. And then I can build my two pipelines, one for each model, and deploy them using the deployment configuration that I specified. And this will actually pull the trigger on getting these models into production, including allocating that hardware, standing up a load balancer, and standing up a web service in front of it. And now at the end of this, I have a fully cloud deployed production service. And if cloud deployment is my ultimate target, I would be done. I can take this URL and hand it off to downstream application teams to consume my models. However, of course, our target is our edge device on our satellite on orbit, and so we need to extend this deployment out to the edge. Now, in order to get this deployed and running on my edge device, there's a couple of additional steps. I'm going to go ahead and define a deployment configuration that represents my edge hardware. In this case, I'm deploying to the Jetson board that is on board the Loft satellite. And so I'm going to specify that my architecture is going to be ARM, and I want to use the Jetson acceleration. As we can see here, using Wallaroo, switching between architectures and acceleration libraries is just a matter of flipping a couple of arguments. This allows me an enormous amount of flexibility when switching from CPU-based to GPU-based execution, as well as when switching between different architectures such as from x86 to ARM and different acceleration libraries and providers. This is going to allow me to target a wide variety of edge devices with my same pipeline very easily. Once I have my deployment configuration for my edge device defined, I can call publish on my pipeline with that deployment configuration in order to package this up as a Docker container to run in a standalone fashion on my edge device. And I can see here the output of this is a bunch of metadata about the container itself, as well as a Docker run command that I can run directly on my edge device in order to get this running. Once I have these artifacts uplinked and running on orbit, I can now turn my attention to the application layer that consumes them. And now we can see here the application code that powers this end-to-end workflow. The first thing that I'm going to do is take advantage of Loft's SDK to actually grab the images produced by my imager. These are actually going to be hyperspectral images by default, so we do a quick pre-processing step to align them into the RGB image our models expect. Next, we call inferences on each of our two pipelines that have been deployed and are running on the satellite. Finally, we ensemble the outputs of those two models in order to create our final result, and then prepare our key package of model predictions and insights for downlink. If we take a look at the two functions we defined here to get inference from our two pipelines, I can see that they contain some pre-processing and post-processing, but ultimately the core component is the inference request that is made of our Wallaroo engine. And these inference requests will be handled by the Wallaroo inference engine that's there on my satellite or any other edge device. And because these are Onyx models, this is going to be powered by the underlying Onyx runtime, and that will be paired with the data processing optimizations that the Wallaroo inference engine includes to enable very efficient inference that is making the most of the hardware that's there on board. And as my model is inferring on orbit and my Wallaroo engine is serving those requests, my Wallaroo deployment is also going to create inference logs to capture the information of what requests have come in and what results were served. These pipeline logs will be downlinked as connectivity and bandwidth allows so that I can centrally manage those deployments from my Wallaroo Operations Center. And I can see here in my Wallaroo Operations Center UI that I can see the two pipelines that are here that make up this overall workflow, and I can click into one of them to see all kinds of metadata about my pipeline, including the specific version number and which ones were actually deployed out to the edge. And if I switch over to the metrics tab, I can see my pipeline inference logs that I had mentioned a moment ago. And so this is going to be a centrally created log that is going to combine any inferences that are happening across cloud and all of my various edge deployment locations. I can dig into these logs from my edge device individually and see what those inferences look like. I can also use these logs to leverage Wallaroo's built-in drift detection capability called assays. Assays are going to allow me to automatically monitor any pipeline input or output for drift. And you can see I've set two up on this pipeline for the average input pixel intensity and the average output confidence. This is going to give me a feedback loop so that I can see if the subject matter that I'm observing on orbit departs from my training data set. That will be reflected in a trigger of drift, as I can see here. Using these logs and assays, Wallaroo is going to allow me to monitor my performance of my edge deployed models so that I can refine them and deploy updates to the edge as necessary. And so today we saw how Wallaroo facilitated this use case of on-orbit ship detection by giving me an easy way to deploy models out to the edge and ensure that I have a healthy feedback loop so that I can monitor what's happening on orbit and refine my models as necessary.